Space is vast and dark. For centuries, we have looked up at the night sky, searching for answers. We've charted the planets. But on October 19, 2017, that quiet certainty was shattered. Something new had arrived from the interstellar void. This event marked the beginning of a profound new chapter in our quest to understand the universe. The object, later named Oumuamua, was the very first interstellar object ever detected passing through our solar system. We had finally met a traveler from another star system. Imagine a message in a bottle finally washing ashore on our small, isolated island in the galaxy. Every piece of data we could gather held the potential to unlock secrets about star systems far beyond our own. It was a silent messenger carrying tales of its journey. Telescopes across the world swiveled to track this mysterious newcomer. The race was on to characterize this object. From the first observations, Oumuamua refused to fit neatly into established categories. It was a cosmic outlier. Its trajectory indicated it wasn't bound to our sun, moving too fast, merely passing through our system. Mysteries deepened as astronomers gathered data. The object's brightness varied dramatically, suggesting an unusual, elongated shape. As it rounded the sun, it showed a slight acceleration, pushing away with an unexplained force. There was no tail or outgassing to explain this push, placing Oumuamua in a class of its own, a scientific paradox challenging our assumptions. Oumuamua, spotted by the Pan-STARRS telescope in Hawaii, means a messenger from afar arriving first. This messenger brought with it more questions than answers. Oumuamua had a reddish hue, suggesting organic molecules baked by cosmic rays. Its high density and lack of cometary outgassing were baffling. Was it a natural object or something else? Could Oumuamua be a piece of technology from another civilization? Its shape, trajectory, and unexplained acceleration were consistent with a manufactured object. The messenger had arrived, but its message remained frustratingly ambiguous. The arrival of Oumuamua ignited debate in astronomy, as the scientific community found itself at a crossroads. Some sought natural explanations, while others considered extraordinary possibilities. Avi Loeb suggested it could be alien technology, like a light sail. This propelled Oumuamua into the public consciousness, forcing us to confront the Fermi paradox. The debate highlighted the nature of science and our place in the cosmos. The story of our first interstellar visitor begins with a whisper. On October 19, 2017, a telescope in Hawaii was scanning the heavens, its mission to detect near-Earth objects. It captured something unique, a faint speck behaving differently, moving with incredible speed. This was Oumuamua. Its speed was far too high for an object belonging to our solar system. Its hyperbolic trajectory was the smoking gun. It was a traveler from the void between the stars. The universe had sent us a fleeting glimpse of something utterly new. Every great discovery has its moment. For Oumuamua, that person was Dr. Robert Warwick. It was his job to sift through the data flagged by the Pan-STARRS telescope. He noted its unusual speed and path. The object's motion was so extreme that it seemed almost impossible. It was coming from a direction high above the plane of the solar system. This was the first interstellar object humanity had ever seen. You are the first person in history to recognize a messenger from another star system. Yet, in doing its job diligently, it stumbled upon something far more profound. His work opened the door to see a visitor from the great unknown. After confirming the interstellar nature of A2017 U1, urgency took hold. It was moving away fast, becoming fainter every hour. This was a once-in-a-generation opportunity. The Discovery team alerted the global astronomy community. On October 25, 2017, the Minor Planet Center announced the object's interstellar origin. The race had begun. Point your telescopes and gather data. The world of astronomy mobilized. They were working against a ticking clock as Oumuamua accelerated away. This meant the information was precious. There would be no second chances. It was a frantic campaign. Telescopes in Chile, Hawaii, and space were used to stare at this faint light. Each photon collected was a clue. The scientific community functioned like a global relay team. It was a beautiful example of worldwide scientific effort. The call to observe Oumuamua was answered with unprecedented enthusiasm. From the deserts of Chile to the mountains of Spain, the world's most powerful observatories turned their gaze towards the departing visitor. The European Southern Observatory's Very Large Telescope, or VLT, located in the Atacama Desert, played a pivotal role. Its massive mirrors were able to capture detailed measurements of the object's color and brightness variations. These observations were among the first to reveal just how strange Oumuamua was. They confirmed that it was reddish, similar to objects in the Kuiper Belt, but its light curve, the graph of its brightness over time, was unlike anything seen before. Other major facilities joined the chase. The Gemini Observatory, with its twin telescopes in Hawaii and Chile, conducted spectroscopic analysis. This technique involves breaking down the light from an object into its constituent colors, like a prism. This spectrum acts like a chemical fingerprint, revealing what the object is made of. Astronomers were desperately looking for the telltale signs of gas or dust that would indicate cometary activity and explain its acceleration. The Gemini data, along with others, came back clean. There was no dust, there was no gas. The mystery only deepened. The object looked like an asteroid, but it was moving like a comet. Even the Hubble Space Telescope, orbiting high above Earth's distorting atmosphere, was called into action. Hubble provided some of the sharpest images and most precise tracking data, while Oumuamua was too small and distant to be resolved as anything more than a point of light. Hubble's keen vision was critical for refining its trajectory. It was Hubble's data that later confirmed the subtle but significant non-gravitational acceleration, the gentle push that could not be explained by the sun's gravity. The space telescope followed the object for as long as it could, tracking it until it became too faint even for Hubble's legendary eyes. The effort was not just about large, professional observatories. Amateur astronomers around the globe also tried to catch a glimpse of the visitor, contributing to the tracking effort and sharing in the excitement of the discovery. The event created a unique bond across the entire astronomical community. It was a shared moment of wonder and challenge. For a few short weeks, a single, tiny, fast-moving object became the most sought-after celebrity in the cosmos. The global response was a powerful demonstration of our collective scientific capability and our shared, innate curiosity about the universe and our place within it. As data poured in from telescopes, astronomers began piecing together a profile of our interstellar guest. The first clue was the extreme variation in its brightness. Its brightness changed dramatically, suggesting a very non-spherical shape. Scientists calculated that Oumuamua must be highly elongated, giving rise to depictions as a cigar-shaped object. Another key clue came from its reddish color, typical of objects exposed to cosmic rays for billions of years. Despite its comet-like trajectory, it lacked a coma. This left astronomers with more questions than answers. Every discovery needs a name. The object, initially designated A2017U1, was discovered by the Pan-STARRS telescope on Maui. The team at Halakala Observatory consulted with Hawaiian language experts. They sought a name reflecting the island's cultural heritage. The name they chose was Oumuamua. The name resonated, replacing the sterile designation with a meaningful identity. Naming it welcomed the envoy from the stars. It recognized Haleakala as a sacred place. The name bridged modern science and Hawaiian wisdom. To understand Oumuamua, we need to look at the Hawaiian language. The name is like a puzzle. U means to reach out for, and mua means first. It means to reach out for in advance, like a scout, or a messenger from far away arriving first. It was the first of its kind from a great distance. This idea of a scout is important in Polynesian culture. These scouts were vital for survival. This name shows its journey had a purpose. A scout arrives first, suggesting others may follow. The name makes us wonder what else is out there. Naming Oumuamua elevated it into a powerful symbol. Our first physical contact with the galactic neighborhood. It was a tangible piece of another star system, a cosmic handshake. The story of Oumuamua captured the public imagination, sparking a global conversation about our place in the universe and the possibility of extraterrestrial life. Oumuamua was a perfect scientific mystery, forcing scientists to be creative. Ultimately, Oumuamua became a mirror reflecting our own hopes and fears about the cosmos, leaving us to forever look at the sky with a new sense of wonder. The legacy of Oumuamua begins with its name, a Hawaiian word acknowledging the cultural context of scientific discovery. The name, messenger from afar arriving first, has become part of our cultural lexicon. The brief observation period provided data that astronomers will be analyzing for decades. It spurred new theories and highlighted the need for a better response system. The debate about its potential artificial origin, while controversial, was valuable. It encouraged scientists to think about what techno-signatures might actually look like. It was a fleeting visitor, a cosmic puzzle that left us with tantalizing clues. The legacy of Oumuamua is a legacy of curiosity, reminding us that the greatest discoveries may still be waiting. As astronomers studied Oumuamua, they began to paint a picture of a bizarre object. One of the first questions was about its size. The object was too small and far to be seen, even by our most powerful telescopes. Scientists inferred its size based on its brightness and how much sunlight it reflected. Calculations suggested it was roughly the length of a city block. This made it a formidable shard tumbling through the darkness. Spectroscopic analysis suggested it was dense and rocky. This picture of a dense, dark object was our first real look at a building block from another star system. Oumuamua was a sample from an entirely different recipe, providing evidence for planet formation elsewhere. The most startling clue to Oumuamua's nature came from how it moved. The resulting graph, a light curve, was unlike anything astronomers had ever seen. Its brightness would swing dramatically. This extreme variation unlocked the secret of its strange shape. To get such a change in brightness, the object's shape had to be extreme. Oumuamua had to be at least 10 times longer than it was wide, more extreme than any known asteroid. This led to the depiction of Oumuamua as a cigar-shaped object. This was a shape that defied easy natural explanation. This was no ordinary space rock. We were dealing with something that had a very different history. Oumuamua's color was a deep brick red, familiar to astronomers as the hue of ancient weathered objects from the outer solar system. This reddish tint comes from space weathering. Cosmic rays and stellar winds transform surface materials into complex organics called tholins, forming a dark crust. The color told us Oumuamua was an ancient traveler, its surface altered by eons in interstellar space. Yet this crust should have sealed in any ices, making its comet-like acceleration even more puzzling. Every clue seemed to contradict another, deepening the mystery. That red hue was the mark of a cosmic wanderer, evidence of a journey across the galaxy. Oumuamua's extreme light curve suggested a bizarre shape, either a long, thin cigar or a flat, disc-like pancake. Both shapes are rare in nature, but the pancake model, possibly a fragment from a shredded dwarf planet, offered a plausible formation. The debate highlighted how little we truly knew. Was it a shard, a splat, or something stranger? Both shapes, thin and streamlined, would travel efficiently through interstellar space. Intriguingly, a flat pancake is also the ideal shape for a solar sail, hinting at even wilder possibilities. The mystery of its shape was inseparable from the mystery of its motion. Oumuamua's form challenged everything we expected from interstellar visitors. Oumuamua's path defied gravity. It accelerated away from the sun faster than physics predicted. Comets do this by outgassing, but Oumuamua showed no coma, no tail, no visible jets. Scientists proposed exotic ideas, invisible hydrogen or nitrogen outgassing, or even sunlight pressure. But only a thin, lightweight object could be pushed enough by sunlight, something like a solar sail. Harvard's Avi Loeb suggested Oumuamua might be artificial, a fragment of alien technology propelled by starlight. This radical idea fit the data odd shape, strange acceleration, no visible outgassing. Whether natural or not, Oumuamua forced us to rethink what's possible in the cosmos. Its motion remains one of astronomy's greatest puzzles. Oumuamua's hyperbolic trajectory marked it as a true interstellar visitor, one passed through our solar system, never to return. It entered from above the ecliptic, swung around the sun, and sped away, too fast for the sun's gravity to capture. Its speed, nearly 59,000 miles per hour, proved it came from beyond our solar system. By early 2018, it was already past Jupiter. By 2022, beyond Neptune, vanishing into the dark. Its origin and destination remain unknown. It's now a faint, unreachable point in the void. For a brief moment, we glimpsed a messenger from another star. Oumuamua reminded us the galaxy is alive with travelers, and we are not alone in the cosmic sea. Oumuamua's mysteries, its acceleration shape and lack of a coma, sparked a scientific race for answers. Most astronomers sought natural explanations, proposing new types of comets, planetary fragments, or exotic ices. Each theory stretched the boundaries of what we thought possible, but all aimed to fit within known physics. The debate showcased the creativity and rigor of science as researchers tested every idea against scant data. If Oumuamua is natural, it hints at a galaxy filled with strange, unseen objects, each with its own story. Solving its puzzle is about more than one rock, it's about understanding our place in a universe of endless possibilities. One of the most intriguing and widely discussed natural theories was the hydrogen iceberg hypothesis. Proposed by astrophysicists Darrell Seligman and Gregory Laughlin, this theory suggested that Oumuamua was a chunk of solid molecular hydrogen. Hydrogen is the most abundant element in the universe, and in the coldest, densest parts of space, like the hearts of giant molecular clouds, it is theoretically possible for it to freeze into a solid. If a chunk of this solid hydrogen were to enter our solar system, it would behave in a way that could perfectly explain Oumuamua's strange behavior. This was a bold and elegant idea, attempting to solve the mystery with a single novel concept. The key to this theory is how solid hydrogen would react to sunlight. As the hydrogen iceberg neared our sun, it would begin to sublimate, turning directly into hydrogen gas. This outgassing would create the gentle thrust needed to explain the non-gravitational acceleration. Crucially, hydrogen gas is completely transparent and invisible to our telescopes. This would explain why astronomers saw the push of a comet but could not see a coma or tail. A hydrogen iceberg would be a ghost comet, its activity completely hidden from view. The theory was compelling because it neatly tied up the central paradox of Oumuamua with one simple, albeit exotic, mechanism. However, the hydrogen iceberg hypothesis faced significant challenges of its own. First, no one has ever seen a hydrogen iceberg. They are purely theoretical objects, and scientists are not even sure if they can form naturally and remain stable. The conditions required to create them are extreme. Second, even if they could form, they would be incredibly fragile. As the iceberg traveled through interstellar space, the subtle warmth of starlight would cause it to evaporate, like an ice cube left on a counter. Calculations suggested that a hydrogen iceberg of Oumuamua's size would not have survived the long journey from the nearest giant molecular cloud. It would have evaporated long before it reached us. Despite these issues, the theory was an important part of the scientific conversation. A related idea proposed that the object was not hydrogen, but a solid nitrogen iceberg, a fragment chipped off a Pluto-like planet in another star system. Nitrogen ice is much more durable than hydrogen ice and could plausibly survive an interstellar journey. It would also outgas invisibly, explaining the lack of a coma. These exotic ice theories demonstrated the lengths to which scientists were willing to go to find a natural explanation. They were willing to imagine objects never before seen, all to avoid a conclusion that was even more extraordinary. Another fascinating natural explanation took a completely different approach. Instead of focusing on what Oumuamua was made of, it focused on how it was built. This was the fractal aggregate or cosmic dust bunny theory. Proposed by astrophysicist Amaya Morrow-Martin, this idea suggests that Oumuamua was not a solid, dense object at all. Instead, it might have been an incredibly lightweight and porous structure, like a giant fluffy snowflake or a cosmic dust bunny. This type of object, known as a fractal aggregate, could form in the outer disk of a star system, where tiny dust grains gently clump together over time. The beauty of this theory is that it solves multiple problems at once. An object that is mostly empty space would be extremely lightweight. Its low density would mean that the gentle pressure of sunlight, solar radiation pressure, could be enough to give it the observed non-gravitational push without any outgassing at all. This would neatly explain why no coma was detected. Furthermore, such a fluffy structure could be easily torn apart and ejected from its home star system, and its elongated shape could be a natural result of the tidal forces that stretched it during its ejection. It paints a picture of a delicate, ethereal visitor, a stark contrast to a dense, rocky shard. This theory, however, also has its own set of difficulties. The primary issue is one of survivability. Would a fragile, fluffy object like a cosmic dust bunny survive the incredible journey through interstellar space? It would have to endure the constant bombardment of cosmic rays and the potential for collisions with micrometeoroids. More importantly, it had to survive its close pass by our sun. The intense heat and gravitational forces so close to our star would likely have torn such a delicate structure to pieces. Scientists who analyzed the trajectory calculated that the object had a certain tensile strength, and it seemed unlikely that a fluffy dust bunny could hold itself together. Despite the challenges, the fractal aggregate theory remains a plausible, if unlikely, natural explanation. It showcases the incredible diversity of objects that might be possible in the universe. It forces us to reconsider our assumptions about what a comet or an asteroid must look like. Perhaps they are not all dense chunks of rock and ice. Perhaps some are as light and airy as spun sugar. Like the other natural theories, it highlights a key theme in the Oumuamua debate. Our first interstellar visitor may have been trying to tell us that our cosmic categories are far too simple and that the universe is far more varied than we ever imagined. While some theories focused on exotic ices or fluffy structures, another compelling line of thought returned to a more violent and rocky origin. Perhaps Oumuamua was not a comet at all, but a planetary fragment, a piece of a world that was destroyed long ago. This theory, explored by scientists like Simon Porteges-Zwart, suggests that Oumuamua could be a shard from a rocky planet or a dwarf planet that strayed too close to its parent star. In this scenario, the star's immense gravitational pull would have ripped the world apart in an event known as tidal disruption. Such a catastrophic event could easily produce elongated fragments and eject them into interstellar space at high speeds. This planetary shard hypothesis has several attractive features. It naturally explains why the object appeared to be a dense, rocky body consistent with the spectroscopic data. It also provides a plausible mechanism for creating its extreme, elongated shape. As the planet was torn apart, the material would be stretched into long, thin filaments before breaking up into cigar-shaped fragments. This violent origin story fits the image of Oumuamua as a tough, monolithic object that could survive a long journey through the galaxy. It suggests that Oumuamua is not just a rock, but a piece of planetary wreckage, a silent testament to a cosmic catastrophe that occurred in another star system. The main challenge for this theory is, once again, the non-gravitational acceleration. If Oumuamua was a dry, inert piece of rock, what could be providing the gentle push? The proponents of this theory had to find a way to incorporate some form of hidden outgassing. Perhaps the fragment still had pockets of trapped ice, like water or nitrogen, buried deep beneath its surface. As the shard tumbled, different parts of its surface would be exposed to the sun, potentially heating these pockets and causing small, invisible jets of gas to be released. This would make it a kind of hybrid object, a rocky asteroid that behaves like a comet. This idea of a messenger from a shattered world is incredibly evocative. It suggests that the space between stars may be littered with the debris of planetary systems, the remnants of worlds that met a violent end. If this theory is correct, then Oumuamua is a geological sample from an exoplanet delivered directly to our doorstep. By studying it, we could learn about the composition and geology of planets orbiting other stars. The messenger's story in this telling is a tragic one. It is the story of a world that was destroyed, and Oumuamua is its silent, tumbling ghost, carrying the memory of that destruction across the cosmos. While most of the scientific community focused on finding a novel, natural explanation, one prominent voice dared to suggest something far more extraordinary. Avi Loeb, a theoretical physicist and then chair of Harvard's astronomy department, looked at the strange collection of facts and came to a different conclusion. He argued that while all the natural explanations were possible, they all required inventing a new class of object that we have never seen before, like a hydrogen iceberg or a nitrogen shard. If we must consider something unprecedented, he argued, why not consider the other unprecedented possibility? That Oumuamua was not natural at all, but an artifact of an extraterrestrial intelligence. This bold claim, often called the alien artifact hypothesis, was not made lightly. Loeb pointed out that Oumuamua's properties were remarkably consistent with what one might expect from a piece of alien technology. Its extreme shape, whether a cigar or a pancake, is not optimal for a natural object, but is very effective for a spacecraft. Its high speed could be the result of being launched from another star system. Most importantly, its slight acceleration away from the sun, with no visible outgassing, is the signature behavior of a solar sail. A solar sail is a proposed type of spacecraft that uses a large, thin membrane to catch the pressure of starlight, much like a sailboat catches the wind. Loeb suggested that Oumuamua could be a defunct or active solar sail, sent by another civilization to explore the galaxy. Its thin, lightweight structure would explain why the gentle push of sunlight was enough to alter its trajectory. It would also explain its unusual shape and why there was no visible coma. All the mysterious pieces of the puzzle suddenly clicked into place with this one radical explanation. He was not claiming to have proof, but rather pointing out that the artifact hypothesis was the most economical explanation, the one that required the fewest ad hoc additions to explain all the observed anomalies simultaneously. This hypothesis was, to put it mildly, controversial. It launched a firestorm of debate within the scientific community and captured the imagination of the global public. Many scientists criticized Loeb for jumping to an extraordinary conclusion without extraordinary evidence. They argued that it was a violation of the principle of Occam's razor, that the simplest explanation is usually the correct one. But Loeb countered that the natural explanations were not simple at all. They required imagining objects with properties we've never seen. The alien artifact hypothesis, while sensational, was a genuine attempt to explain the data, and it forced the scientific community to confront a question it often prefers to avoid. The debate over Oumuamua was a clash of scientific philosophies. One side followed Occam's razor, favoring the simplest explanation. Most astronomers assumed Oumuamua was a natural object. To assume an alien civilization was a monumental assumption. Avi Loeb and others used probability, considering the universe's scale. With billions of stars, it's statistically improbable we're alone. Perhaps Oumuamua was the life we've been searching for. The debate became a discussion about evidence, knowledge limits, and the possibility of not being alone. It was about our place in the cosmos. As the world's leading space agency, NASA was naturally at the forefront of the response to Oumuamua. Its powerful assets, like the Hubble Space Telescope and the Spitzer Space Telescope, were instrumental in gathering the crucial data that revealed the object's strangest properties. NASA-funded projects, including the Pan-STARRS survey that made the initial discovery, really formed the backbone of the entire observational campaign. The agency served as a central hub for coordinating and analyzing the flood of information coming from observatories around the globe. Yet, when it came to interpreting this data, NASA adopted a position of careful and deliberate scientific conservatism, a stance that would guide the official narrative surrounding our first interstellar visitor. From the outset, NASA's public statements and scientific publications emphasized the search for a natural explanation. The agency's experts acknowledged the deep mysteries presented by Oumuamua. They confirmed its interstellar origin, its strange shape, and its puzzling non-gravitational acceleration. However, they consistently framed these anomalies as challenges to our current understanding of astrophysics, not as evidence for extraterrestrial technology. NASA's official position was that Oumuamua was a natural object, albeit a very strange one, and that its peculiarities would eventually be explained by new models of comets or planetary formation. This approach really reflects the agency's core mission, to advance scientific knowledge through rigorous, evidence-based inquiry. This cautious stance was best exemplified by the work of scientists at NASA's Jet Propulsion Laboratory, or JPL. These experts are masters of celestial mechanics, calculating the trajectories of spacecraft and natural bodies with incredible precision. It was their analysis of Hubble data that definitively confirmed Oumuamua's anomalous acceleration. Yet in the very same paper that announced this stunning discovery, the authors explored various natural outgassing scenarios as the most likely cause. They were careful not to stray into speculation about artificial origins, sticking strictly to what could be modeled and tested within the known laws of physics. For NASA, the burden of proof for an extraordinary claim remained extraordinarily high. This measured approach was crucial for maintaining scientific credibility, but it also placed the agency in stark contrast to the more speculative theories gaining traction in the public sphere. While headlines buzzed with talk of alien probes, NASA remained the calm, authoritative voice, reminding everyone that science is a marathon, not a sprint. The agency's position was clear. The discovery of Oumuamua was a revolutionary moment, but it was the beginning of a new scientific inquiry, not the final answer to the question of whether we are alone. The truth, they argued, would be found in data and peer-reviewed research, not in sensationalism. While debate continued about Oumuamua's origins, some scientists took a direct approach, listening. If it was alien technology, perhaps it wasn't entirely silent. The Breakthrough Listen project, dedicated to finding intelligent life, used the Green Bank telescope to listen for signals. The campaign was methodical, scanning billions of radio channels for artificial signals. After weeks of analysis, the result? Silence. No signals were detected, but the effort demonstrated our ability to respond to potential techno-signatures. The brief, tantalizing visit of Oumuamua served as a powerful wake-up call for the astronomical community. It proved that interstellar objects are not just a theoretical possibility, they are a reality. And it really highlighted a critical weakness in our capabilities. We were caught completely by surprise. We only spotted Oumuamua when it was already on its way out of the solar system, giving us just a few precious weeks to study it. The consensus was clear. We needed to be better prepared for the next one. The legacy of Oumuamua, therefore, is not just the data it provided, but the powerful impetus it gave to developing the next generation of tools to find and characterize its successors. The most direct impact was on the development of new and more powerful sky survey telescopes. The Pan-STARRS telescope that found Oumuamua was just a precursor. The true game changer is the Vera C. Rubin Observatory, currently under construction in Chile. When it comes online, this observatory will conduct a survey of unprecedented scale and depth, imaging the entire visible sky every few nights. Its massive camera and sophisticated software are expected to find not just one interstellar object per decade, but potentially several per year. The Rubin Observatory is, in many ways, an Oumuamua finding machine, designed to give us the one thing we lacked in 2017 advance warning. This promise of early detection has ignited serious discussions about a rapid response mission. Scientists and engineers at NASA and other space agencies are now exploring concepts for a spacecraft that could be kept on standby, ready to launch at a moment's notice. The idea is to intercept the next interstellar visitor, fly alongside it, and study it up close. Imagine getting high-resolution images of such an object, or even landing a probe on its surface to analyze its composition directly. This is the dream that Oumuamua inspired. Projects like the European Space Agency's Comet Interceptor are already in development, designed to do just that for a long-period comet. But the technology could be adapted for an interstellar target. The visit of Oumuamua has fundamentally shifted the priorities of planetary defense and near-Earth object studies. While the primary goal remains finding potentially hazardous asteroids, there is now a much greater emphasis on finding all faint, fast-moving objects. The scientific goldmine represented by interstellar objects is simply too valuable to miss. Oumuamua demonstrated that the sky is full of surprises, and it has spurred a new era of investment in the infrastructure needed to find them. It ensured that when the next messenger arrives, we will be ready and waiting to receive it. Few scientific discoveries break out of the laboratory and capture the collective imagination of the public quite like Oumuamua did. It was a story that had all the elements of a great science fiction classic: a mysterious visitor from a distant star, a bizarre and unnatural shape, and behavior that defied easy explanation. The controversy ignited by the alien artifact hypothesis, championed by a Harvard professor, propelled the story from the science pages to the front pages. Oumuamua became more than just a data point. It became a cultural phenomenon, a shared global moment of wonder, speculation, and debate. The name itself, melodic and meaningful, helped it stick in the public consciousness. News programs, documentaries, and magazine articles dissected the mystery for a mainstream audience. The object became a popular subject for podcasts, YouTube videos, and social media discussions, where amateurs and experts alike could debate its origins. The striking artist's impressions of the space cigar became iconic, a visual shorthand for this cosmic enigma. Oumuamua entered our cultural lexicon as a symbol of the profound and unanswered questions about our place in the universe. It was a story that made everyone, from children to grandparents, look up at the night sky with a renewed sense of awe. The story of Oumuamua also served as a powerful catalyst for conversations about science and the scientific process. The public was given a front-row seat to a real-time scientific debate. They saw how scientists propose theories, challenge each other's assumptions, and slowly work towards a consensus, or in this case, an impasse. The clash between the cautious, methodical approach of NASA and the bold speculation of Avi Loeb illustrated the healthy tension that drives scientific progress. It was a masterclass in how science works, complete with all its uncertainty, controversy, and excitement. It showed that science is not a dry collection of facts, but a dynamic and deeply human endeavor. Ultimately, Oumuamua's greatest cultural impact may be the sense of possibility it reignited. For a brief moment, the idea of contact with an extraterrestrial civilization felt less like a distant fantasy and more like a tangible possibility. Whether Oumuamua was a rock or a spacecraft, its visit forced us to confront the vastness of the cosmos and the potential for life beyond Earth. It sparked curiosity and inspired a new generation to become interested in astronomy and space exploration. The messenger may have departed, leaving its secrets intact, but it left behind a powerful and enduring legacy, a renewed sense of wonder and a reminder that the universe is still full of mysteries waiting to be discovered. Our story began with a whisper in the dark. Oumuamua's journey was brief, yet its impact will resonate for decades. It was more than just the first interstellar object we had ever seen. It was a profound scientific catalyst. Oumuamua shattered our neat categories of comet and asteroid, highlighting both our incredible ability to detect faint objects and our desperate need for a faster response. It now feels like an inevitable next step in our exploration of space. It forced the scientific community to seriously consider what an alien artifact might actually look like. The messenger has left us with a new mandate: to keep our eyes, our instruments, and our minds open. As Oumuamua journeys back into the void, it leaves us changed. In 2019, Borisov's discovery fulfilled this promise. We now know the galaxy sends a variety of objects. Our task is to build the nets to catch them, to catalog their properties, and piece together their story. The journey ahead requires patience, vigilance, and readiness for the next surprise. Each object is a precious clue to understanding distant star systems. This search answers fundamental questions. Are we alone? Oumuamua sparked curiosity and reminded us of our shared cosmic home. The messenger has departed, but its mission, a challenge to science and imagination, was a success.